this lecture, we are going to start our voyage in the ocean of solving optimization problems. The statement of the optimization problem in the entire course is very simple, which is as follows. Find a minimum of a sufficiently many times differentiable function of n variables in the entire n-dimensional Euclidean space or in a particular region of the n-dimensional Euclidean space. In solving such a general optimization problem, Yuri Nestorov, an internationally recognized person for optimization methods and a Dantzig Prize winner, commented in his famous book entitled Introductory Lectures on Convex Optimization that in general optimization problems are unsolvable. Although by imposing a simple condition of continuity on the objective function and closedness and boundedness on the constraint set, there is a guarantee of existence of a solution to the general optimization problem. But identification of a solution to the general optimization problem is not really a piece of cake. What is very fascinating that the methods for solving a few particular optimization problems, like for linear optimization problems or for convex optimization problems, are so vast and elegant today that across the globe several universities are going to open departments of decision sciences or departments of operations research where exclusively the existing methods for particular optimization problems will be employed. In order to systematically approach for identification a solution of the general optimization problem, we require a few basic notions from linear algebra and calculus. In this lecture and in the next lecture, we shall recall a few concepts from linear algebra that are required in the entire course. Thereafter, we shall recall a few concepts of calculus. Those will be employed in the entire course. The tools from linear algebra that we shall describe in this lecture are the concepts of vector space and subspace of a vector space. Then the concepts of linear dependence and linear independence of a set of vectors will be discussed. With the help of linear independence of a set of vectors, the notions of basis and dimension of a vector space will be described. Thereafter, the notions of norm and inner product will be discussed. Norm is a generalization of the length or magnitude of a vector. Inner product is a generalization of dot product of two vectors. Next, we will discuss the concept of Euclidean projection of a given vector on a given particular subset of the n-dimensional Euclidean space Rn. Finally, we will discuss the concepts of eigenvalues and eigenvectors of square matrices with real entries. Let's start our discussion with the idea of vector space. What do we mean by a vector? From our basic knowledge about vectors, we know that a vector is a quantity that has a direction and a magnitude or length. Typically, a vector v in the three-dimensional Euclidean space is presented by v1 I hat plus v2 j hat plus v3 k hat, where I hat, j hat and k hat are unit vectors along the x-axis, along the y-axis and along the z-axis respectively. We also present the vector v with the help of three coordinates v1, v2 and v3, where v1, v2 and v3 are called as components of the vector v along the x-axis, along the y-axis and along the z-axis respectively. If there is no confusion, we commonly remove this upper arrow bar to present this vector. That means we simply use the notation v to present it. We are all familiar with the notions of addition of two vectors and scalar multiplication with a vector. Not only that, we are also aware of a few properties of addition of vectors and scalar multiplication with a vector. The properties that we are all aware of are as follows, that if we are given three vectors u, v and w in the three-dimensional Euclidean space, and if we are given two scalars alpha and beta, then regarding addition of vectors, we know that if we consider the addition of u and v, we get a vector in the three-dimensional Euclidean space. If u is being added with v, then we get a vector identical with v being added with the vector u. If u is considered to be added with the resultant vector of the addition of v and w, then we get a vector which is identical with u plus v being added with the vector w. We have a very special element, the null vector or the origin in the three-dimensional Euclidean space, for which we all know that if u is being added with the null vector, we get the same vector u. Corresponding to every given vector u, there exists a reverse of the vector which we denote by negative u, for which we have the property that if u is being added with the reverse of u, we get the null vector. These are five properties of addition of vectors. These five properties are true for every given u, v and w in the three-dimensional Euclidean space. Regarding the scalar multiplication with vectors, we all know that if we take scalar multiplication alpha with a vector u, we get a vector in the three-dimensional Euclidean space. If we consider to take alpha times beta u, then we get a vector identical with alpha beta times the vector u. We also have distributive property that alpha plus beta times u is equal to alpha u plus beta u, and alpha times u plus v is equal to alpha u plus alpha v. We have a very special element 1 in the real number set, for which we all know that 1 times any vector u gives us the same vector u. These are five properties that we are all aware of regarding scalar multiplication with vectors. These five properties are true for every given scalars alpha, beta, and every given vectors u and v in the three-dimensional Euclidean space. These 10 properties altogether are so fundamental that with the help of these 10 properties, we define abstract vector spaces over the scalars taken from the real number set. We call a non-empty collection of elements, capital V say, a vector space over the real number set R if corresponding to every given u, v and w inside the set V, we have all these 10 properties. This axiomatic definition of abstract vector spaces was possibly given by the mathematician G. Peano, and not necessarily always scalars for a vector space are to be considered from the real number set. We can even replace this real number set over here by an abstract set, capital F say, which is called as a field, and any element inside a field is called a scalar, and when we are replacing this real number set by a field, we will say that V is a vector space over the field F instead of over the real number set. If you are interested to know the historical genesis of the development of vector space theory, you may visit this particular article written by Dorier from France. And if you are interested in learning abstract vector spaces, you may visit a fascinating book by Hoffman and Kunz entitled Linear Algebra. If, however, you are interested in geometrical essence of linear algebra, you may please visit the treatise by Gilbert Strang and this book entitled Higher Algebra by my esteemed and mostly revered teacher, Professor S.K. Mapa. When we consider an abstract vector space capital V over an abstract field capital F, in that case we denote the vector space by capital V first bracketed capital F. Any element of the field capital F is called a scalar and any element of the vector space capital V is called a vector. So we now got to know the general definition of a vector. By a vector we mean an element of a vector space. We shall now consider a few examples of vector spaces from where we shall see that even polynomials or continuous functions or matrices can also be treated as vectors. When the underlying field to define the vector space capital V is just the set of all real numbers, we shall just drop out this notation capital F to be used. We shall use simply capital V to denote a vector space over the field of set of all real numbers. Let us now consider a few examples of vector spaces. The first example is our familiar n-dimensional Euclidean space, which is given by n tuples where each ai is a real number. This set of all n tuples is a vector space over the field the set of all real numbers, where addition of two elements in Rn is considered component wise, that means in the usual way of adding two n tuples, and the scalar multiplication with an element in Rn is also considered component wise. Another example of a vector space is set of all polynomials with real coefficients and having degree strictly less than n, where a0, a1 till an minus 1 are real numbers. This set of all polynomials having degree strictly less than n together with the zero polynomial or the zero function forms a vector space over the set of all real numbers, where the addition of two polynomials is done in the usual way and scalar multiplication with the polynomial is also done in the usual way. Another example of a vector space is set of all matrices of order m by n whose entries are all real numbers, which is a vector space over the field of all real numbers, where the addition of two matrices is taken in the usual way and scalar multiplication with a matrix is also taken in the usual way. Another example of a vector space is the set of all real valued continuous function defined on the closed and bounded interval a to b, which is a vector space over the set of all real numbers where the addition of two functions f and g is given by ft plus gt and scalar multiplication with a function is given by c times ft, where this c is a real number and these compositions are for every t inside the set of all numbers in the closed and bounded interval a to b. Now notice that as vector is an element of a vector space, so a polynomial can be treated as a vector, a matrix can be treated as a vector, even a continuous function can also be treated as a vector. However, in the entire course, we shall not deal with vectors, those are polynomials or those are continuous functions. We shall deal with only the vectors in the n-dimensional Euclidean space. Next, we shall describe the concept of subspace of a vector space. Let capital V be a vector space, a non-empty subset W of V is called a subspace if the elements in capital W forms a vector space with respect to the composition of vector addition as it was for the vector space capital V, and with respect to the composition of scalar multiplication with a vector as it was in the vector space capital V. That means with respect to the same compositions, those were in capital V, the elements in capital W, if forms a vector space, then W is called a subspace of the vector space capital V. That means the elements in capital W should satisfy all the 10 axioms to define a vector space. We notice that as the elements in W are already elements of capital V and capital V is a vector space, out of all these 10 axioms, except the first and sixth axioms, rest of the axioms are automatically satisfied by the elements in capital W, and therefore in order to become a vector space, the elements in W must satisfy only the properties or axioms first and the sixth, that is, if W1 plus W2 belongs to capital W and alpha 1 times W1 belongs to capital W for all W1, W2 in the set capital W, and for all scalar alpha 1 in the real number set. In fact, these two conditions can be presented in a compact manner just by only one condition, that alpha 1 W1 plus alpha 2 W2 belongs to capital W for all scalars alpha 1 alpha 2 and W1 W2 in the set capital W. Let us consider a few examples of subspaces of the vector spaces R2 and R3. Notice that if we consider capital V to be the R2 plane and capital W as the set of all vectors x1, x2, those are line in a line passing through origin. Let's suppose x2 is equal to 2x1. In fact, you consider any constant m, then this W can be shown to be a subspace of the vector space capital V. As an example of subspace of the vector space, the three-dimensional Euclidean space, we can show that set of all elements in capital W forms a subspace of the vector space capital V. I am keeping these two examples as home task to verify that these two sets W's in these two examples are satisfying this condition. In fact, we can show that any line passing through origin in the 3D space is also a subspace of the three-dimensional Euclidean space. If, however, we consider a line in the 3D space that does not pass through origin, then that line is not a subspace of the three-dimensional Euclidean space, because any subspace of a vector space must contain the null vector of its parent vector space. This is due to the condition of becoming a subspace. In this condition, we notice that if we take the values of alpha 1 and alpha 2 to be zeros, then this vector is a null vector, and therefore any subspace of a vector space must contain the null vector of its parent vector space. Next, we shall describe the idea of linear combination of vectors. You know, this expression of defining subspace of a vector space is known as a linear combination of the vectors W1 and W2 for some given scalars alpha 1 and alpha 2. You might wonder why the term linear is associated with the term linear combination. The geometrical reason behind this is as follows. In our high school level, we have learned some axioms for lines and planes. One of those axioms is, if a plane contains 2 points A and B, say, then it also contains the line joining these 2 points A and B. This axiom expresses the intuitive notion of flatness. Non-planar surfaces do not satisfy this property. For example, if we take a sphere and then consider 2 points on the surface of the sphere, then the line joining those 2 points is not lying on the surface of the sphere. A surface in the n-dimensional Euclidean space is crudely called geometrically linear if it contains all of the lines through the points of the surface. Note that the set of vectors is geometrically linear because if u1 and u2 are two elements in this set, then the line joining u1 and u2, that is this set, lies entirely inside this particular set. As this set of vectors gives geometrically a linear or flat surface or a planar surface, the expression of this type is called a linear combination of the vectors w1 and w2. In general, for a set of n vectors u1, u2 till un, a linear combination of them is the expression alpha 1 u1 plus alpha 2 u2 plus so on till alpha n un for some scalars alpha 1, alpha 2, alpha n. Next, we shall describe the notion of linear dependence and linear independence of a set of vectors. We notice that in this expression of linear combination of the vectors u1, u2 till un, if we take the values of alpha i's all zeros, then we get the null vector. So null vector is always a linear combination of any given few vectors. In case this equation is true for at least one alpha I not equals to 0, then we call the vectors u1, u2 till un as linearly dependent. If however, if this equation is true only for all alpha i's are equals to 0, then we say the set of vectors u1, u2 till un linearly independent. These are the definitions of linear dependence and linear independence. We notice that if a set is linearly dependent, then that set is not linearly independent and vice versa. These two definitions of linear dependence and independence are applicable for a set of finitely many vectors. If we have a set of infinitely many vectors, then we notice that this equation for defining linear dependence or independence has left hand side an infinite sum. In order to avoid equating an infinite sum with the null vector, we define linear dependence of a set of infinitely many vectors in the following manner. A non-empty set capital S, a subset of a vector space, is called linearly dependent if there exists a finite subset of S which is linearly dependent. Linear dependence of a finite set is defined by this manner that we have defined over here. For linear independence of an infinite set, we define it by the negation of linear dependence of an infinite set. We call an infinite set linearly independent if capital S is not linearly dependent. That is, if every finite subset of capital S is linearly independent. Let us now consider one or two examples on linear dependent and linear independent sets. Let us consider two vectors. Let's suppose 1, 2 and 2, 1 from the R2 space. Let us check whether this set is linearly dependent or linearly independent. To check it, we consider the equation for linear dependence where alpha 1 and alpha 2 are real numbers. Let us check whether this equation has solution only 0 or some non-zero solution does exist. We see that this equation is valid only if alpha 1 is equal to 0 and alpha 2 is equal to 0. Therefore, this set is linearly independent. If we consider, however, this example, say the set consisting 1, 2 and the vector 2, 4, then we see that we have this equation equals to 0 is valid for any real numbers alpha 1, alpha 2 satisfying alpha 1 equals to minus 2 alpha 2. So this equation has a non-zero solution. For instance, we consider alpha 1 equals to minus 2 and alpha 2 is equal to 1, and hence this set is linearly dependent. Let me give you a home task to check linear dependence of a set of vectors from the three-dimensional Euclidean space. You consider this set and check whether this set is linearly dependent or independent in the three-dimensional Euclidean space. You will find that this set is linearly independent. Quite often we abbreviate this term linearly independent just by Li. Next, we shall describe the concept of linear span of a given set of vectors. For a given set of vectors, say capital S, from a vector space capital V, the linear span of the set capital S is the smallest subspace of the vector space capital V containing the set S. Linear span of the set capital S is usually denoted by L of S. It can be shown that if the set S is finite, then the linear span of S is the set of all linear combinations of the elements in S. That is this set. Here we see that this set LS is a subspace of the vector space capital V. If we see that a subspace capital W is a linear span of some set capital S, then we say the set S is a generator of the subspace W or of the subspace LS. This is due to the fact that as if all the elements in LS are generated by the elements in S, which can be explicitly realized from this expression. We notice that if S is finite, then in that case every element in LS is just linear combination of the elements in the set S, and thus capital S is called a generator of this set LS. For an example of linear span and generator, we consider the set capital S, say the set of vectors consisting 1 0 0, 0 1 0 and 0 0 1 from the R3 space, then we see that any element in LS is given by this expression for some alpha 1, alpha 2, alpha 3 in the real number set. And hence we see that this LS is nothing but the entire three-dimensional Euclidean space R3, and therefore this capital S is a generator of the three-dimensional Euclidean space. As an advanced example, consider the set S as the set of three vectors from R3 space, and so that any element in R3 space can be expressed as a linear combination of these three vectors, and hence this set S can also act as a generator of the R3 space. With the help of the notions of generator and linear independence, we shall now discuss the idea of basis of a vector space. A set of vectors, say capital S, from a vector space capital V is called a basis if the set S generates the vector space V and the set capital S is linearly independent. For example, the set of vectors 1 0 and 0 1 constitute a basis for R2 space. The set of vectors is a basis of the R3 space. In fact, we can also show that this set of vectors is linearly independent in the vector space R3 and generates the entire vector space R3 and hence a basis of R3. From these two examples, we see that bases of a vector space may not be unique. The bases in these two examples are called the standard basis of the vector space R2 and R3 respectively. In general, for the Rn space, the set of n vectors u1, e2 till en, where ei is n tuples consisting all elements are zeros except one at the ith place, is called the standard basis of Rn space. The number of elements or cardinality of a basis of a vector space is called the dimension of the vector space. Due to this definition of dimension of a vector space, we notice that this R2 space has dimension 2, R3 space has dimension 3, and the Rn space has dimension n. This mathematically validates the term dimensional in two-dimensional R2 space, in three-dimensional in R3 space, n-dimensional in Rn space. This word dimensional we have been using even in this lecture, and we have been using from our high school level. And here we got to know the definition of dimension. Next, we shall discuss the concept of norm of a vector, which is a generalization of the length or magnitude of a vector. So far, how did we measure the length of a given vector, say OP, where P has the coordinate x1, x2 till xn, this n tuple. We are assuming this P is a vector in the n-dimensional Euclidean space. To measure the length of this vector OP, we commonly have used the Euclidean distance from the point O, which is the origin, to the point P. That is, the length of this vector OP is identified by the square root of x1 square plus x2 square plus till xn square. However, practically, in order to reach from the point O to the point P, we may have certain obstacle over here, and therefore to reach at the point P from the point O, we might have to take a path of right angle like this. Now question comes, how much is the distance of this feasible path to reach at the point P from the point O? To measure this distance, we require a generalized notion of distance of a given point P from the origin of the underlying vector space. And this generalized distance from origin to a given vector is known as norm. Mathematically, norm is defined as follows. Mathematically, norm is a non-negative function defined on a vector space V which satisfies the following properties. The first, that norm of any vector x is a non-negative quantity. Norm of a vector is equal to 0 if and only if the vector is the null vector. Norm of alpha x for some alpha scalar or real number is equal to modulus of alpha times norm of x, and norm of x plus y, where x and y are two vectors from capital V, is less than equal to norm x plus norm y. This inequality in the fourth property is called triangle inequality, because if we consider x and y as two sides of a triangle, then we know that the other side of the triangle is given by the vector x plus y, and for a triangle we know that addition of two sides of the triangle is always bigger than or equals to the length of the third side of the triangle, and that's why this inequality is called Triangle inequality. A vector space capital V together with a norm defined on it is called a norm space. With the notion of a given norm, we can define a generalized notion of distance between 2 points, say x and y. If 2 points x and y are given in the n-dimensional Euclidean space Rn, then this vector joining x and y is given by, we all know, that y minus x. The norm of this vector y minus x measures the length of this vector joining x to y. This norm y minus x is called a generalized distance between the points x and y. Let me give you a few examples of norms in the n-dimensional Euclidean space. The first example is the Liebig 1 norm or the L1 norm, which is denoted by norm subscripted 1. We notice that these two vertical bars usually is the denotation of a norm. Norm 1 in the n-dimensional Euclidean space is defined by norm of x1, where x is having the coordinates x1, x2 till xn, which is an element in Rn. This norm of x1 is equal to modulus of x1 plus modulus of x2 plus till modulus of xn. You may please verify that this norm x1 satisfies all these four conditions to becoming a norm. Next example is the L2 norm or the Liebig 2 norm or the usual Euclidean norm, which is denoted by norm subscripted 2 and given by. Next example is the Liebig P norm for p greater than equals to 1, a real number. This norm p is defined by modulus x1 to the power p plus whole to the power 1 upon p. Next example is the infinity norm or the maximum norm, which is denoted by norm subscripted infinity and defined by. Let me give you one example of a norm in the CAB space, norm of x, where obviously this x is a vector in this space and hence x is a function, real valued continuous function whose norm is given by maximum over the closed and bounded interval a to b modulus of the function values xt. Let me also give you a few examples of norms of matrices or norm in the vector space of all M by N matrices with real entries. The first example is the maximum column norm. Norm of a matrix capital A is given by maximum over, where this matrix A is a matrix of order M by N and its entries are Aij's. This norm is called maximum column norm, and here we subscripted 1. This is due to the fact that this norm 1 of the matrix capital A is eventually associated with this L1 norm. We shall not go into details of how this L1 norm is associated with this norm 1 for matrices. If you are interested, you can look at any book of functional analysis. Next example is the infinity norm of a matrix, which is given by maximum over. This infinity norm of a matrix is also called maximum row norm because we notice that this quantity finds the sum of absolute values of all the entries of the ith row. You compute now all these m quantities corresponding to the m rows of the matrix A and then find maximum of all these m entries. You will get the infinity norm of the matrix A, and thus it is called the maximum row norm. Another example of matrix norm is the 2 norm of a matrix, which is given by lambda max of the matrix A transpose A whole to the power half, where this lambda max is the maximum eigenvalue of the matrix A transpose A. We shall describe what is an eigenvalue of a matrix later in this lecture. If capital A is a symmetric matrix of order n by n, then this expression of norm A2 reduces to maximum over absolute values of all the eigenvalues of the matrix capital A. Next, we shall discuss the concept of inner product in a vector space over the field of all real numbers. Inner product is a generalization of dot product of two vectors. Like dot product, a function of two vectors that gives output as a real number. Similarly, inner product is also a function of two vectors. That means a function that is defined on the Cartesian product of a vector space capital V and gives output as a real number, which satisfies the following conditions. The first condition, that this function is symmetric, that means inner product of two vectors u and v is same as the inner product of the vectors b and u. The second property is that for three vectors u, v and w, the inner product of u and v plus w is equal to inner product of u and v plus inner product of u and w. This property is called linearity property of the inner product. The third property is that for any given scalar alpha u inner product with v is equal to alpha times the inner product u and v, and also this must be equal to the inner product of u and alpha v. This third condition is called the condition of homogeneity, and the fourth condition is that inner product of the same vector u and u is a positive quantity for every non-null vector u in the vector space capital V. A vector space together with an inner product defined on it is called an inner product space, and a vector space over the field of all real numbers together with a real valued inner product is called an Euclidean space. From this term real valued inner product, you might wonder that there might exist inner product which is not of real valued. Yes, there are. For a general definition of inner product, you may please visit the book by Hoffman and Kunz that I have mentioned earlier in this lecture. Let me give you a few examples of inner products in the n-dimensional Euclidean space. The first example is the standard inner product of u and v, where u and v are two vectors in the n-dimensional Euclidean space Rn, and u and v are the n tuples u1, u2 till un for u, and for v, v1, v2 till vn. One inner product of u and v is the usual dot product u1 v1 plus u2 v2 plus till un vn. We can show that this expression satisfies all these four properties of inner product, and hence this expression gives an inner product in the n-dimensional Euclidean space Rn. Here I have used this term quite often, n-dimensional Euclidean space. We have gone through why the term dimensional. Now here we have gone through the term why Euclidean, because this Rn vector space is a vector space together with at least one inner product that is of real valued. Let me give you an example in the form of a home task, so that this expression where u and v are two tuples in the R2 space is an inner product in abbreviated form IP in R2. So this one, that means you verify all the four conditions of becoming an inner product. We see that in the first example, if we take inner product of the vectors u and the same vector u, then we get the expression that u1 square plus u2 square plus till un square, which is nothing but the norm of u square with the L2 norm, and therefore norm u2, L2 norm of u is positive square root of the inner product of u and u. This phenomena is not just a coincidence. We can even show that if we define a function positive square root of the inner product of u and u, this function is a norm in the vector space V for any given inner product in the vector space capital V, and therefore any inner product space is a norm space, because corresponding to any given inner product we can define a norm in the vector space. Here I would like to ask you a question. We have seen here that corresponding to any given inner product we have a norm, whether the reverse is always true or not. That means corresponding to every given norm, can we have an inner product? The answer for this is negative. Corresponding to every norm, we may not have an inner product. The acid test for whether a norm can be obtained from an inner product is the parallelogram law, which states that if u and v are two vectors in a Euclidean space, then norm of u plus v square plus norm of u minus v square is equal to twice norm u square plus norm v square. This equality is referred as parallelogram law due to the fact that if we take u and v as two sides of a parallelogram, then we see that the diagonals of the parallelogram are given by u plus v and u minus v. Therefore, the lengths of the diagonals are norm u plus v and norm u minus v. Now, from the well-known fact that for a parallelogram, sum of the square lengths of the diagonals is equal to twice of the sum of the lengths of two adjacent sides, which is precisely this equation, and thus this equation is referred as the parallelogram law. This parallelogram law can be easily proved by expanding this norm u plus v square as inner product of u plus v and u plus v, and expanding this norm square as inner product of u minus v and u minus v. Now you expand these two inner product expressions, you will get the right hand side, and therefore if a norm is given by inner product, then this parallelogram law must be satisfied by that norm. Hence, if a given norm is not satisfying this parallelogram law, there does not exist any inner product from which this norm can be identified. An example of a norm that cannot be derived from an inner product is the example of the maximum norm in the space of CAB. To justify that this norm is not given by an inner product, you consider two vectors x1t is equal to the constant function 1 and x2t is equal to the function t for all t inside the closed and bounded interval 0 and 1. Say here I am taking a as 0 and b as 1. Then you find norm x1, norm x2 and norm of x1 plus x2 with norm of x1 minus x2. Then you show that these two vectors x1 and x2 does not satisfy the parallelogram law. We shall wrap up this section of inner product and norm by mentioning one of the widely used inequality in optimization, that is the Cauchy-Schwarz inequality, or more appropriately Cauchy-Bunyakovsky-Schwarz inequality, which states that for any two vectors u and v in a Euclidean space, modulus of the inner product of u and v is less than or equal to norm u into norm v. The equality holds only when u and v are linearly dependent. This inequality was published by Augustin Louis Cauchy in 1821, and the corresponding inequality for integrals were published by Bunakovsky in 1859 and by Hermann Sauerge in 1888. Next, we shall discuss the notion of Euclidean projection of a particular point in the n-dimensional Euclidean space Rn on a non-empty subset of the n-dimensional Euclidean space Rn, which is defined as follows. An Euclidean projection of a point x bar on a non-empty set capital S in Rn is a point that achieves the smallest Euclidean distance from x bar to the set capital S. That is, Euclidean projection of the point x bar is a solution of the optimization problem minimum of x minus x bar with the Euclidean norm subject to x lying in the set capital S. Let us execute an example to find Euclidean projection. Find the projection of origin in R3 on the plane capital S given by. To find the Euclidean projection of origin on this set capital S, the corresponding optimization problem is minimization of norm x, where x is subjected to 2x1 plus x2 minus x3 is equal to 1. Here obviously this x is having three coordinates x1, x2, x3. We shall solve this problem from the geometrical viewpoint because we do not know so far how to obtain solution of a constraint optimization problem. We see that we need to minimize this distance norm of x2, and corresponding to every given positive constant k, norm x2 is equal to k gives us a spherical region centering at origin and having radius k. If this is the location of the plane capital S, then minimum value of norm x2 on this plane is obtained when the radius of the sphere is such that this sphere touches the plane capital S. Then that touching point of this sphere must be giving us the projection of origin on the set capital S. Obviously then at this point this plane S touches this particular sphere, and hence this is perpendicular to the sphere capital S. So what it turns out that the projection of origin on S is such a point on the plane capital S such that this vector OX star is perpendicular to the plane, and therefore X star is parallel to the vector 2, 1, minus 1, which is perpendicular to this plane. Now setting X star is equal to some scalar multiplication of 2, 1, minus 1, the equation of the plane 2x1 plus x2 minus x3 is equal to 1 gives us alpha is equal to 1/6, since this x star is a point in this plane, and hence x star is equal to 1/3, 1/6 and minus 1/6. Let us now execute another problem in which we will consider two generic vectors. We consider to find the projection of a non-zero vector or non-null vector v in Rn on the ray of another non-zero vector u in Rn. That means geometrically It is asking us to find the projection of the vector say v on the ray of the vector u. Here this point is the origin of Rn. Obviously the projection of this point v is such a vector on u that this vector is perpendicular to this particular ray. As this vector is given by some scalar alpha times u, obviously this vector is given by v minus alpha u. From the condition of the vector v minus alpha u is perpendicular to the vector to the ray of the vector u, we get this inner product is equal to 0. As in dot product, we know that if two vectors a and b are perpendicular, then their dot product is equal to 0. Similarly, if the inner product of two vectors is equal to 0, then we say that the vector a is perpendicular to the vector v. From the condition of perpendicularity of v minus alpha u with u, we get this equation. From here, we see that the value of alpha is given by inner product of vu divided by the inner product of u and u, and hence this projection point of the vector v on the ray of u is given by inner product of vu divided by norm u square times the vector u. We shall wrap up this section of projection by mentioning three important results regarding projection of a vector over a particular subset of Rn. The first result is regarding projection of a point on a closed and convex subset of Rn. By a closed subset of Rn, we mean a set for which the complement of the set is such that for any point z inside the complement, there exists at least one sphere centering at z which entirely lies inside the set SC. For example, if we consider a triangular region consisting all the points inside this triangle and the boundary of this triangle, then we notice that its complement satisfies this property. Or if we consider a circular region in the R2 plane consisting all the points inside the circle and the boundary, then also we notice that this condition is satisfied, and therefore this triangular region or a circular region are closed sets in the R2 plane. By a convex set in Rn, we mean a set S in Rn for which whenever two points u and v in capital S, the line segment joining u and v also entirely lies inside the set S. For instance, we consider this triangular region or this circular region, they are convex sets. However, if we consider a region of this type, say in the R2 plane, then we notice that we have 2 points u and v for which the line segment joining them is not entirely lying inside this set, and hence this set is not a convex set. For a non-empty closed convex set, the result regarding the projection is as follows. If S is a non-empty closed and convex set in Rn, then for every x bar outside the set S, there exists a unique point in S that is closest to the set S. That is, geometrically, if x bar is a point outside a closed convex set, say this set, then there exists a unique projection from the point x bar on the set S. As this projection point is unique corresponding to any x bar outside the set capital S, we can define a projection function for the set S as follows. Ps x bar is equal to the unique minimum point of the distance from x bar. That is, PS x bar is equal to minimum of norm z minus x bar over z belonging to the set capital S. A fascinating fact regarding this projection on a closed and convex set is that reverse of this result is also true, which states that if capital S is a non-empty closed subset of Rn, and if for every x bar there is a unique projection, that is Euclidean projection, then the set capital S is a convex set. We shall end up this section of projection by mentioning a formula of the projection of a point on a set of linear equalities that states that the Euclidean projection of a point x bar on the set, that is given by a set of linear equalities where A is a matrix of order m by n with real entries and B is a column vector of order m by 1, is given by the definition of projection that minimum of norm x minus x bar of 2 norm. Eventually we can consider its square also, and even we can multiply with a constant, say half, subject to Ax is equal to B, whose solution is given by x star is equal to, here obviously we are assuming this matrix capital A is a flat matrix, that means the number of rows m is less than equal to the number of columns, and also we are assuming that this matrix has rank is equal to m. But how is this formula coming cannot be perceived just by inspection. We need optimization theory to be applied over here, and on a later lecture of this course we will see that this solution is correct with the help of the Karush-Kuhn-Tucker optimality condition. Now next we shall describe the final topic of this lecture, that is the topic of eigenvalues and eigenvector of a square matrix. By an eigenvalue or a characteristic value of a square matrix of order n by n with all entries real, we mean a root of its characteristic equation. By characteristic equation of the matrix A, we mean the equation determinant of A minus xin, where in is the identity matrix of order n, is equal to 0. Here x is a real variable. If the matrix A is having entries aij's, then we notice that this characteristic equation is given by the determinant of this matrix, which is the same matrix capital A except the diagonal entries as a11 minus x, a22 minus x, and the nth one is ann minus x. We note that for a given square matrix of order n, its characteristic equation is given by a polynomial of degree n, where this C0 is equals to minus 1 to the power n, and this Cn is obviously the determinant of the matrix capital A. Since this characteristic equation is an equation of degree n, it will have n roots, and not necessarily all these n roots are real, even if all these entries aij's are real. Any root of this characteristic equation is called a characteristic value of the matrix capital A or an eigenvalue of the matrix capital A. The word eigen is having a German origin whose English equivalence is own. This term eigenvalue or characteristic value is possibly due to Augustin Louis Cauchy, who used the term Racine characteristic U while classifying quadratic surfaces in the early 19th century. The English equivalence of this term Racine characteristic U is characteristic root, for what we now call it as eigenvalue. The term characteristic in characteristic root is still survived in the term characteristic equation. Well, coming back to this characteristic equation, we have mentioned that even if all entries of the matrix capital A are real, not necessarily all the roots of this equation are real. If, however, the matrix capital A is symmetric, then we can prove that all the roots of its characteristic equation are real. That is, all eigenvalues of a symmetric matrix are real. This fascinating result for a symmetric matrix is also due to the great mathematician Cauchy. Let us now quickly compute eigenvalues of a matrix of order 2 by 2. Let us consider the matrix capital A is equal to, its eigenvalues are given by the equation determinant of this matrix is equal to 0, which simply gives us x is equal to -1 or 7, and therefore eigenvalues of the matrix capital A are -1 and 7, which are both real numbers. If, however, we would have considered the matrix capital A is equal to, say, the matrix 0 -1 1 0, then we can simply notice that the eigenvalues of capital A are both purely imaginary numbers, iota and minus iota. Let me give you a home task here to identify eigenvalues of a matrix of order 3 by 3. Say capital A is equal to 1 -1 0 1 2 -1, and the last row is consisting 3 2 and -2. Find its characteristic equation and show that its eigenvalues are 1 1 and -1. We shall now discuss the concept of eigenvectors of a square matrix. We notice that a matrix capital A broadly acts as a transformation, that for any given vector x, if we multiply a square matrix of order n by n on x, then we get another vector y in Rn. So when we act capital A on the vector x, we get another direction or another vector y. Commonly, the direction of y and the direction of x are different. If, however, x is such a non-null vector that the vector ax is parallel to x, that is, the direction of ax is same as that of x or its reverse direction, then we call such a non-null vector x as an eigenvector of the matrix capital A. That is, mathematically we define eigenvector of a matrix capital A as follows, that a non-null vector x in Rn is said to be an eigenvector of the matrix capital A with all entries real if there exists a real number lambda, so that Ax is equal to lambda times x. Geometrically, this scalar lambda can be thought of as a stretching factor, that before the action of capital A, the length of the vector x was this much amount, and after the action of A, the length of the vector is this much amount, where this vector is lambda x. So earlier the length of the vector was norm x, and after the action of capital A, the length of the vector gets modulus lambda times norm x. So this lambda value can be thought of as a stretching factor by the action of the matrix capital A. By a simple inspection, we can see that if X is an eigenvector of the matrix capital A, then X can be obtained by solving this equation Ax minus lambda x is equal to 0, or this system of equations A minus lambda in times x is equal to 0 for some real number lambda. As x is a non-null vector, this homogeneous system is having a non-null solution, and therefore the determinant of the coefficient matrix must be equals to 0, and hence this lambda is a solution to, and hence lambda must be an eigenvalue of the matrix capital A. So corresponding to every eigenvector, there exists an eigenvalue of the matrix capital A. Here let me place a question before you. Corresponding to every eigenvector of A, there exists an eigenvalue, but whether this eigenvalue is unique or not. That means, is it possible that corresponding to a given eigenvector x of the matrix capital A, can there exist two eigenvalues lambda 1 and lambda 2, so that Ax is equal to both lambda 1x and as well lambda 2x? Answer to this question is obviously negative due to this part of this equation. As x is a non-null vector, we must have lambda 1 equals to lambda 2. Otherwise, lambda 1x can never be identical with lambda 2x, and therefore corresponding to a given eigenvector of a matrix capital A, there exists a unique eigenvalue of the matrix A. Now let me place another question before you, that if lambda is an eigenvalue of the matrix capital A, can we ascertain that there exists an eigenvector of the matrix A, so that Ax is equal to lambda x? The answer to this question is trivially affirmative. Yes, we can assure it due to the simple inspection that as lambda is an eigenvalue of the matrix capital A, then obviously lambda is a solution to this equation. Therefore, this system A minus lambda in times x is equal to 0 is having a non-zero solution, and a non-zero solution x to this system evidently satisfies Ax is equal to lambda x, and hence this non-zero solution to this system is an eigenvector corresponding to this given lambda. Let me ask you another question, that whether every square matrix with real entries is having an eigenvector. Answer to this question is negative, because the components of an eigenvector must be all real, as we are considering all the entries of this matrix are real, and we are considering here the underlying field of our discussion as the field of all real numbers. By considering this matrix capital A of order 2 by 2, we have earlier seen that this matrix has eigenvalues iota and minus iota, which are purely imaginary numbers, and therefore you will not be able to identify any non-null vector x with real entries, so that Ax is equal to some scalar times x. If however you would have considered this matrix capital A as a matrix in the field of all complex numbers, you will find that this matrix is having an eigenvector. We shall now consider a simple 2 by 2 matrix. We shall now consider a simple 2 by 2 matrix and get to know how to compute eigenvectors of a matrix. Consider the matrix capital A as 1, 3, 4, 5. Since corresponding to every eigenvector, there must be an associated eigenvalue. To compute an eigenvector of this matrix, at first we compute its eigenvalue, and then with the help of a given eigenvalue, we will go for computing an eigenvector. Eigenvalues of this matrix capital A is given by the equation 1 minus lambda t 4 and 5 minus lambda is equal to 0, which will give us lambda is equal to minus 1 and 7. Now corresponding to this lambda equals to minus 1, let us suppose x is equal to x1 x2 is an eigenvector of the matrix capital A. Then evidently by the definition of eigenvector, we must have Ax is equal to lambda x, which is minus x, and hence this equation gives us this system of equations, which is further giving us x1 is equal to minus 3 by 2 x2, and hence this eigenvector x is given by x2 times minus 3 by 2 and 1, where x2 is a non-zero real number. Any vector of this type, some non-zero constant times minus 3 by 2 and 1, is a solution to this system Ax equals to lambda x, and hence this x is an eigenvector of the matrix capital A corresponding to the eigenvalue lambda equals to minus 1. Now corresponding to lambda equals to 7, let me give you a home task. Show that eigenvectors corresponding to lambda equals to 7 are given by some scalar c times the vector 1, 2. I now end up this lecture here. You know, this concept of eigenvectors is pioneered by Leonhard Euler and Joseph Louis Lagrange, who used the concept of principal axis to study rotational motion of rigid bodies. Lagrange realized that the directions of principal axis are the eigenvectors of the inertia matrix for the rotational motion of a rigid body. To geometrically sense the importance of the direction of eigenvectors, let me give you a home task that you consider the equation of an ellipse, say x1 square divided by 4 plus x2 square divided by 9 is equal to 1. Then corresponding to this left hand side expression, find a matrix of order 2 by 2 so that this left hand side expression is equal to x transpose qx, where x is the vector x1 x2, and then find the directions of the eigenvectors of this matrix capital Q and check that those directions of eigenvectors are nothing but the directions of major axis and minor axis of this ellipse. I stop this lecture here. On the next lecture, with the help of this eigenvalue, we will attempt to characterize positive definiteness of a square matrix of order n by n. This notion of positive definiteness of a square matrix will be later extensively used to identify convexity of a given function of several variables. Thank you all for all of your kind attention.